and welcome to Aerotech's Automation 1 Motion Control Platform Educational Series. Aerotech is a company that solves your toughest precision motion and automation challenges. Automation 1 is a motion control platform consisting of software-based controls and development tools, PC and drive-based control hardware, and hardware-based drives for servo motors and other devices. In this video, you'll discover what PSO is, how it is used, and how to configure it. We will also introduce you to some example programs as well as some advanced PSO features such as Part-Speed PSO. My name is Alex Smoker, and I'm a Control Systems Specialist for Aerotech. So what is PSO? Well, PSO stands for Position Synchronized Output. This is a feature that allows you to control a drive output, such as a digital output, in response to the position feedback signal of one or more of your axes. In other words, this allows us to track an encoder signal and trigger an output pulse based on the position of that encoder device. For this, Aerotech allows you to do up to 3 dimensions of position feedback tracking given the proper drive hardware options. The benefit of doing this is that it allows for position-based tracking and laser firing rather than time-based firing. This in turn gives you the confidence of more consistent and repeatable laser firing and no bunch up near the corners of your parts, since we are not trying to time the laser pulses. We are instead just firing the laser based on specific position intervals. Now, one of the advanced PSO features we will also discuss is called Part-Speed PSO. This will have its own category. As opposed to tracking a position feedback signal like an encoder, Part-Speed PSO actually tracks the velocity command of an axis. And because Part-Speed PSO is based on tracking a command rather than needing a feedback device, Part-Speed PSO can then be used for more complex operations such as using PSO when the encoder feedback is either nonlinear or even non-accessible. This includes, amongst other things, the ability to track virtual axes. So take, for instance, if the X, Y, and Z part space commands of a system are being modified by some sort of kinematic transformation, such as a 3-axis galvo or hexapod system. Part-Speed PSO would be able to track this XYZ axis command operating within this part space of the tool rather than trying to track the encoder sources themselves. Alternatively, because Part-Speed PSO is based on this velocity command, this also lets you utilize some PSO features when either the encoder hardware for PSO is unavailable, or you're using a traditionally non-compatible PSO feedback device, such as an absolute encoder without incremental signal capabilities. But enough on that, we are going to be going into Part-Speed PSO in more detail later. Alright, now let's dig in and figure out how PSO generally functions. We will use this diagram to explain how basic PSO functions. In its most basic form, PSO simply watches the encoder device and then outputs a pulse based on that position. But in reality, it is a little more complicated than that. Essentially, we have what we call modules for each PSO function and operation. Each of these dictates either how the PSO is going to be configured or how it will react before getting outputted from the Automation 1 drive. First, we have the event modules. These are what generate the PSO events based on various conditions and circumstances. These events are broken up into 3 categories: distance events, window events, and laser events. Distance events allow the PSO to track the encoder and cause an event based on moving a certain distance. Window events allow the PSO to track an encoder and cause an event based on either entering or exiting a specified region. And finally, laser events, which are a little more unique and are caused by triggering the output via special galvo scanner commands. After the event module, we have the waveform module. This is what determines what happens to a drive output after some condition is met and the event module is triggered. This comes in 3 sizes as well: pulse, PWM, and toggle. Pulse is your traditional PSO method. This will cause simple pulses with a specified on time to occur on the drive output every time an event happens from the event module. PWM will modulate the output based on an array of user configurable on times and varying duty cycles. The last one, the toggle mode, will simply cause the output waveform to toggle on or off each time an output event from the event module occurs. And finally, we then have the output module. This module specifies which physical output PSO pin is actually being driven. Now, as you may have noticed, I did skip a step in the diagram. Before the waveform module, we technically have another module called the bit module. I do not have this highlighted since we wanted to explain the basics of PSO first. In essence, though, this module can be used as a secondary input into the output module, bypassing the waveform module completely. Or it could be used as another way to mask the events from the event module before getting inputted into the waveform module. but we are going to go into all of these in more detail next. Before we do that, however, I do want to stress the difference here between what we call the event module and output events. The term event is used twice here, but in different contexts, and this becomes important as we move into how PSO actually functions and how we explain it. Just be aware that when we say, for instance, that an event happened or that an event was generated, we are generally referring to this event module where the condition for PSO was met. Or to put it another way, an output that the controller queues up to be ready to be outputted but has not actually been configured via the waveform module yet. This could be something as simple as the fact that we have moved 1 millimeter and the system is ready to fire another pulse. Saying an event occurred does not necessarily mean that a physical drive output from the drive has happened, only that the controller is telling the drive that something happened and we want to fire another pulse. The output event, or sometimes just called the drive output or pulse event, is the physical output from the drive. Okay, so starting first with the event modules, let's look at the different types. First up are the distance events. The distance events generate your output pulses based on the vector distance traveled by one or more of your axes. So for instance, like we see in the image below, events will occur every time that an axis has moved a certain distance. Again, I want to reiterate that the distance module outputs these events based on the vector distance. So if we are tracking two or more axes, it is actually the vector move that we are tracking and firing based upon. We accomplish this by utilizing three internal tracking counters that essentially mirror the encoder signal that the drive is seeing. These counters are technically what the PSO is actually tracking. In Automation 1, Aerotech allows you to track up to 3 axes at once to allow for both single axis, dual axis, or triple axis vector tracking. One crucial thing we need to mention here is that, like most PSO command implementations, we utilize encoder counts as the frequency method for outputting events. So for instance, we do not say trigger every 1 micron. Rather, we say trigger the event based on the encoder count equivalent of what 1 micron is. This distance event module also supports the use of the drive array to output PSO events using an array mode, thus allowing output events with non-uniform sequences at specific encoder locations. This drive array is a concept that will come up often enough with PSO, so we'll briefly touch on it now. In essence, it is just a general internal array that Automation1 uses for various PSO purposes where the information can be stored. For the distance event module, it is where we can store a list of our specific encoder locations that we want to fire at using the array mode. Now, moving on to the window events. The window events generate your output pulse using a range of 2 position values, i.e. what we call a window. Each window consists of a counter and 2 comparison values, a lower bound and an upper bound, that we track using more internal counters. In this case, similar to the distance event, we track the window using 2 internal counters specific just for the windows. In the normal use case, the output of the PSO window module is active when the window counter value is greater than or equal to the lower bound and also less than or equal to the upper bound. The PSO window module allows you to configure and use 2 windows simultaneously using the 2 different window counters. These would be what we call window number 0 and window number 1. Now, when using these 2 windows, the output of each window is combined to form a single PSO window output. In the normal use case, this means that the PSO window output will only be active when both individual window outputs are also active. In other words, when both window counters are within their respective window bounds. Most commonly, these window events are used to mask our distance events. In fact, this is what we are seeing in our image below. Here, we set up the distance event module to occur twice every 4,000 encoder counts. However, we also have a window range that is masking all of these distance events that occur when we are outside of this specific window. This example is probably the best visualization of what we were talking about earlier regarding the difference between events from the event module and a physical drive output event. In this situation, the events generated from the event module are always occurring every 4,000 encoder counts, regardless of if the physical output event happens or not. But only the events within our window are actually output events or pulses, or drive outputs as you may hear. Finally, similar to the distance event module, the window module can also utilize the drive array to implement a sequence of various window ranges using the array mode. So we aren't just limited to a single window range that we can set up. We can have multiple arrays of different varying window ranges. And last but not least, finally we have our laser event. This event module generates an output event each time the galvo laser output turns on. Now, this Galvo laser output is actually a separate set of programming commands made specifically just for the Aerotech Galvo scanners. These program commands allow you to specify various things like the Galvo's pulse width, standby period, or allowable on times. Without going into more detail on the Galvo commands themselves, they simply add more functionality for the high-speed Galvo controls and outputting some kind of laser or pulse from the drive. So these Galvo output commands can be synchronized in a way with PSO as an additional way to tweak the Galvo controller's laser output feature. Alright, with that said, let's now jump over and look at the waveform module a little bit more in detail. As we mentioned before, this is where we can control what happens to the event from an event module before it actually gets sent to the physical drive output. This includes things like the pulse width as well as how many cycles of pulses can happen per event that occur from the event module. We will look at these functions more in depthly during our examples. Within the waveform module, we have three configurable options: pulse, PWM, and toggle. The pulse mode is what we have been seeing in our example snippets so far, and this is the most common use case. This will set up the PSO to output a pulse with each output from the event module. Each of these pulses will contain a total time for the pulse, a specified on time within the aforementioned total time, and then the number of pulses that actually get outputted per event from the event module. So once an event occurs, we can configure the total time for the output pulse, how long the actual output will be on for each pulse, and then the number of pulses that actually occur per event module event. The PWM mode is similar to the pulse mode, but with a few additions. As opposed to being a fixed total time plus on time plus number of pulses scenario, the PWM mode utilizes the drive array to load a series of various duty cycle values. In this mode, you specify your total time per event, then the on time values are specified as an array. This on time is then what modulates your duty cycle. Essentially, at each event from the event module, the PWM mode changes what your on-time pulse length will be for the next pulse in your sequence. Finally, the toggle mode will cause the output waveform to toggle on or off each time an output event from the event module occurs. So each time an event occurs from the event module, the toggle mode will switch between turning the physical output on and turning it off. Finally, now let's talk about this glossed over bit module that we mentioned in our diagram before, because this can be used as a powerful tool at times. This module can be placed in between the output module and the waveform module, either as an additional mask to the output events or as a way to bypass the waveform module completely. This bit module allows you to specify a sequence of binary values, either 1 or 0, known as bits, to directly drive the PSO output module on or off at the corresponding events. At each subsequent event, the bit module then updates the next bit value stated in a sequence that you specify using AeroScript commands. This is what we're seeing in our example here. We have the distance event module set up to create an event every 1000 encoder counts, and then we then set up different bit values to follow the sequence on, off, off, on, off, on, off. At each of these distance events, we set the physical drive output to the next value that we previously configured in our sequence. So at 1000 encoder counts, we turn the output on. At 2000, we configured it to turn off. Then at 3000, we left it in the off state. And then at 4000 counts again, we turned it back on. So you can see how we are combining the distance module to generate events every 1000 encoder counts, then utilizing the bit module to trigger what each of those events cause the drive output to actually do. Do they turn the output on or off? In a situation like this, we're actually bypassing the waveform module completely, since we don't actually need to configure what the on time, the total time, or the number of cycles is going to be. We are simply saying at each of these sequences every 1000 encoder counts, do we set the drive output on or do we turn it off? Next, we want to give a quick mention of Multiaxis PSO as its own section here. As we touched on before, PSO utilizes internal tracking counters that track the position feedback of your axis, and this is no different in Multiaxis PSO. This is why we included this section, just to give you a better visual representation and conceptual idea of what Multiaxis PSO is actually doing. And here we can see a good representation of this in our image. Here we can see the single counter, counter number 1, being used for tracking a single axis one-dimensional move. Then, as we move into 2 or 3 axis tracking, more counters are added to give us that 2 or 3-dimensional encoder tracking, but it is still tracking that vector distance, where that distance is equal to the square root of the sum of each of our encoder counters squared. So next on our list is reviewing the PSO specifications and restrictions. First, the restrictions. For one, as of right now, we cannot track absolute encoders that do not also use an incremental signal. Some absolute encoders are just the absolute encoder signal, while some come along with a secondary incremental signal. If that absolute encoder has an incremental signal along with it, we can use that to track and fire using PSO. Secondly, we cannot use the PSO features with the MX1 hardware option. To be clear, this only applies when we are actively using the multiplier option for an analog encoder. This is simply due to the method of hardware encoder multiplication that Aerotek uses with this MX1 option. Fear not though, because the other encoder multiplier options that Automation1 drives offer do allow for PSO functionality with analog encoder signals. Last but not least, virtual PSO. You cannot use PSO virtually except with the part-speed PSO functions. Traditional PSO requires the use of a physical encoder signal for Automation1 to actually track. Without this, PSO will not function. The solution for virtual PSO testing or operation will be to use the part-speed PSO functions. This will allow you to, quote, track the encoder signal because the part-speed PSO looks at the velocity command of an axis, not the actual position feedback signal, so no actual physical position feedback signal is needed. Next on our list, we have the tracking limitations of PSO. Each event module has a limitation on how quickly it is actually able to track those internal counters and the encoder signal itself. For all but the laser event type, this limitation is 100 MHz, or 100 million encoder counts per second. This is universal amongst single, dual, and triple axis PSO. The reason that the laser event type does not have the limit is because it is not actively tracking an encoder signal like the other two. Again, remember the laser event module simply outputs a PSO event based on a separate command from the Galvo commands. If you do, however, start exceeding these limitations, then you will start to lose encoder counts, and therefore you will get incorrect PSO firing. So it is always important to make sure that we are trying to stay under this 100 MHz limitation while trying to track an encoder. Now, in the event that you do need to move and track an encoder faster than the 100 MHz allowed, we do have some solutions. The first is that you could simply slow down the feed rate of your axis. This will in turn lower your input rate. But this solution is not always viable or desired since it reduces your overall throughput. To keep your throughput and prevent a loss of encoder counts, we can also use another common parameter setting. The one stipulation here is that this parameter only applies to analog sine wave encoders using a PSO compatible multiplier option. So the solution to this 100 MHz issue is to utilize the primary emulated quadrature divider parameter. This will effectively decrease the resolution of the quadrature signals that PSO is tracking. Now, this does not mean that the resolution of your stage is actually reduced. This simply reduces the resolution of those internal tracking counters to allow for a faster axis movement while still providing accurate PSO tracking. You can determine if you need to use this parameter based on this equation, where your maximum encoder input frequency is equal to your maximum speed in user units times your counts per unit axis parameter. For reference, this counts per unit axis parameter is what does the actual conversion from encoder counts to user units in the axis configuration. If this value you calculated is above 100 MHz, then it is advisable to use this primary emulated quadrature divider parameter. If you do end up needing to use this parameter, make sure that you also divide your firing distance by that same divider amount. So, imagine a scenario where you are trying to fire your PSO every 10,000 encoder counts, and you are also moving your stage at 20 million encoder counts per second. Your fixed PSO distance here is fine. However, clearly you are exceeding that maximum input rate of 100 million counts per second, or 100 MHz. To get the effective 200 million encoder counts per second under the 100 MHz limit, we could implement a primary emulated quadrature divider parameter with a value of 4. This brings our effective resolution, i.e. what the PSO internal trackers are seeing, down to 50 million encoder counts per second, well within our allowable range. We still have a problem by doing this though. Because we effectively changed our PSO tracking resolution, this also changes our user unit firing distance as well. This is what we are seeing in our images here. If we only implemented the emulated quadrature divider, we could see that we are still attempting to fire every 10,000 encoder counts. However, our user unit distance increases because we changed the resolution of what the PSO trackers are interpreting. That is what we see in the image on our left. So essentially, when you use the emulated quadrature divider parameter for PSO without dividing the distance firing event by that same amount, it actually becomes a multiplier when you look at the firing distances through the lens of your user units. The image on the right demonstrates that after we divide our original firing distance by that same divisor of 4, everything normalizes and we are back to firing at our original intended 1 mm distance. I hope all of that makes sense, since this is a big component when using an analog sine wave encoder with PSO. Now what about the drive limitations? How fast can we actually output pulses from our drives? Well, this is going to depend on the drive itself. So for all that information, I'd highly recommend reviewing your drive's hardware manual. In the case of the Automation1 XC2E drive, for instance, this limitation is either 12.5 MHz or 5 MHz, depending on which physical drive output type is actually being used. So if you were to review your drive's hardware manual, you will find that there is a page on different PSO hardware connections. Depending on which one of these you use will determine the maximum output rate that the drive can actually handle, which segues us into physical wiring. For this, you will again need to review the drive's hardware manual, but a sample for the Automation1 XC2E can actually be found here, where we see both TTL and isolated outputs are supported. Last but not least, latency. Each drive or PSO configuration is going to have a latency associated with it. This represents the delay between when the drive is told to fire, i.e. the output pulse, and when we physically get an outputted pulse from the drive. This is going to be determined by a number of factors. First, the drive itself. Each drive will have its own latency values based on the hardware connection method that we touched on earlier, so either TTL or isolated outputs. Second is the PSO type. Single axis PSO tracking will have a different latency than dual or triple axis PSO tracking. And third, if the encoder multiplier is actively being used on the encoder or not. In the case of the individual drive latencies, you'll just have to look in your drive's hardware manual. For our XC2E example, though, the TTL output provides a 5 nanosecond latency. For single axis tracking, the added latency is plus 40 nanoseconds. Dual and triple axis PSO has then a 50 nanosecond latency. Finally, if you're using an encoder multiplier, this adds another 800 nanoseconds of latency to the calculation. So going through a quick example of this, here we have a situation where we have dual axis PSO. We are then wired to a TTL driven output on an XC2E drive, and we are using an encoder multiplier on top of all of that. So what is our latency? Well, we can see in the hardware manual for an XC2E that there is a 5 nanosecond latency for the TTL output. Add the 50 nanosecond and 800 nanosecond latencies from the dual axis PSO and encoder multiplier, and we come out with a total of an 855 nanosecond output latency for the drive. Next up, let's briefly touch on the programming side of things with PSO. Again, the first thing to mention is that the PSO operates based on encoder counts, not user units. Secondly, each module in the PSO flowchart has its own set of programming commands. The distance event module has its own commands, the window event module has its own commands, and the waveform module has its own commands. If you were to follow your process through each step in the PSO flowchart, you should end up using each of these modules' individual programming commands for setting up each of those sections. So doing a PSO distance event plus a window event mask through the waveform module and then finally onto the output module should end up using the distance event, the window event, the waveform module, and then finally the output module commands. But I won't bore you with all these different types of program commands and their syntaxes. Just know that if you plan on using the PSO commands, make sure that you have the correct module's commands configured. This should help make it easier if you're trying to navigate the help file and figuring out which commands you still need for what you are trying to do with PSO. If you are interested, however, I would recommend reviewing the Automation1 help file for a more in-depth look at the different program commands and their syntaxes. Next on the docket, we are going to run through some simple PSO examples just to give you something to test out and look at. In addition to that, to show you that we are actually firing a pulse, we are going to be using the Visualize workspace in Automation1 to plot our PSO output pulses. Alright, so here is going to be our program, and like I said, we're going to just be doing a simple single one-axis fixed distance PSO firing. So I have most of the program already pre-filled out here, and so we're just going to be walking through and filling in some of the blanks. So just starting at the top and working our way down. For the simplicity of the example, we're just going to home and enable, and then the one important thing is resetting the PSO. Again, remember, PSO works on the idea of using internal trackers and counters to keep track of where the stage is at and when to fire. We're just going to be resetting all of that for a fresh start when we do this example. Now, as we can see down here below, we do have it split up into our distance waveform module and output module chunks. So we have to go through and set up each of those separately. So for the first one, this is just going to be which axis are we tracking? And we're going to be doing the x-axis. And more specifically, we're going to be doing the x-axis primary feedback. So using the IntelliSense here, let's just scroll down until we find the XC2E primary feedback input. So that should tell us to track the main 25-pin D connector on the front of the XC2E controller. Next is going to be the fixed distance. How often are we actually going to be firing? So again, we have to specify the x-axis, and then here's where we're actually going to be using this units to counts feature to fill in the gaps and just make it a little easier to read and tell it what to do. So essentially what this is saying is the units to counts is going to convert whatever 10 units or 10 millimeters in my case is in encoder counts for the x-axis, and then use that as the number of encoder counts to fire based on. So if we were not using units to counts, what you would actually have to do is go into your configure workspace, figure out what your counts per unit is, and then multiply that by the number of units you wish to use. So in our case, we're telling it to fire every 500,000 encoder counts. Next, we simply have to enable the counters for PSO distance and enable the event module itself. So we're both doing that for the x-axis, and that basically finishes up what we have to do for the PSO distance event. We've set up what encoder we're tracking and how often we plan on firing. So next, we actually have to set up how the waveform itself, what the actual pulse is going to look like in what it's doing. So again, we're going to be doing the x-axis, and because we're just doing a simple single axis firing, we're going to be using the pulse mode. Again, if we were just doing something like pulsing it automatically, would be a PWM, and if we just planned on toggling it each time the PSO distance events went off, we'd be using something like toggle. In this case, we're just doing, we want to fire every time the PSO distance event goes off, so we're just going to be using pulse. Next, we have to configure the total time of the pulse. So each time the distance event happens and we make that pulse, how long of a time do we want this pulse to occur for? And for this, we're just going to do 20 milliseconds. So keep in mind, like I said, this is 20 milliseconds, but the value you actually enter here is in microseconds. Now, what we also have to do is enter in how long we actually want the output to be on for during this total time. So the total time is simply specifying what range of time do you want the pulse output to be before it does the next pulse in the series here, as we'll get to later on, with the how many pulses to occur. So the fixed on time is simply telling you how long do you want the pulse to be physically on for on the output. And for that, we're going to do 15 milliseconds. Now for the pulse fixed count, essentially what this is, how many of these output events do you want to occur per pulse that happens? So once a pulse from the distance event occurs, how many of those 20 millisecond, 15 millisecond pulses are going to occur or are going to happen? So in this case, each time this event happens, each time our distance counter hits 10 units, 10 millimeters, and fires an event, we're going to see 3 sets of 20 total millisecond on fixed times with a 15 millisecond on time. Now, after we get that set up, we simply have to apply the configuration and enable the waveform. Again, both on the x-axis. Finally, we have to set up the outputs. So where's the source for the output coming from, and what pins are we actually using? So let's configure our source. Again, we're coming from the waveform. And then as our output, what pin do we actually want it to come out on? Now for our uses, we're just going to be using the dedicated output that the XC2E has. If you were using some kind of other controller, there might be multiple PSO outputs that you could do that are supported, and so you just have to select which one you physically planned on wiring up to. Now, as our final set of programming commands here, we're simply going to be turning on data capture, making a move, and then turning that data capture off so we can see what's happening. Now, I already have the PSO configure signals configured, so what we're going to be doing is we're going to be seeing the position feedback, we're going to be looking at the PSO counter itself, and then we're going to be seeing the actual output status. So we'll be able to track and see through the digital scope what the PSO is doing and see if that corresponds to what we expect it to do. All right, let's go ahead and run. So again, as mentioned with the PSO fixed distance, every 10 units, every whatever encoder counts that equates to, is when we fire the PSO event, and that's all captured using an internal counter. So this PSO counter 0 is that internal counter. So we start at 500,000 encoder counts. Given the resolution of the plot, that is what it is going to be. At this point, my resolution is maybe not high enough to show exactly 500,000, but it gives you the good idea. After we run through those 500,000 or every 10 millimeter, the pulse event happens, or this distance event happens, and then it resets and it starts tracking again. So we can actually put our cursors roughly where each events occur and see how closely that corresponds to how often we told it to fire. So we did tell it to fire every 10 millimeters, and here we are seeing 10 millimeters. What actually is happening at the PSO output status, though, and see how close that actually corresponds to what we told it to do. So again, if you remember, what we told it to do was do 3 sets of 20 milliseconds total time with a 15 millisecond on time per set. So if we put our cursors here and here, this is the first set. We can see the second set is here, and then the third set is right here. So it's 3 sets per firing event that occurred. And we could also see that this total time is indeed 20 milliseconds. And if we put it on our on time, that it is indeed 15 milliseconds. Now, without hooking up an oscilloscope and showing you with some kind of camera what physical output it's connected to, you'll just have to believe me that it's wired up and connected to the dedicated output. But hopefully that should give you a quick overview and idea of what the PSO programming looks like and what we actually expect to see on the plot here. If this program here is taken out of the help file and is just a slight modification of that, so if you want to run through that, you can do so. Make sure you set up your correct drive outputs and encoder count firing, and just modify and play with some of the values and see how that corresponds in your plot below. All right, let's go ahead and jump over to looking at a window example and seeing if we can make some masking happen and just show you what happens when we use PSO windows in conjunction with maybe the distance to mask those distance events. All right, so after a quick jump cut, we have our PSO window event example here ready. I just built this based on our previous example that we just went through with some few minor additions. So first, I reduced the firing event to every 0.5 millimeters. This is just to give you a better understanding, better idea visually of what the window is doing. I also added preemptively the PSO window commands that we're going to need. So again, which input we're using, which encoder signal we're tracking essentially, what our range is going to be, and then turning it on and enabling the PSO window output. On the waveform module setup, all I did was reduce the total time to 2 milliseconds from 20 milliseconds, and my pulse on time from 15 milliseconds to 1.5 milliseconds. Again, this was just to compensate for the shorter pulse time or the shorter pulse distance that we're using for fixed distance. Otherwise, if we start trying to overlap our pulses, we're going to be seeing missed firing events and inaccurate firing. Otherwise, everything else was kept the same. So let's go ahead and quickly configure our PSO window settings. So again, we're still doing this on the x-axis. We're going to select which window we're going to use. Again, this could be two simultaneous windows at the same time, but we're just doing a single one window. And then we're going to configure which input we plan on using. So again, which hardware input do we want to use to look at this? And like before, we're just going to be using the XC2E's primary feedback device. Finally, the last one is simply reversing direction. Which direction do you plan on the window counter planning on counting in based on its feedback source? And for that, we don't need to work with that any right now, so we're just going to do false. So next is the range. And again, we're going to select the x-axis, Windows 0, and we're going to do the units to counts function just to make things simple. So we're going to set up our window range from 3 millimeters to 5 millimeters. So we'll be able to see that in the example in our plot, that our window is going to be between 3 and 5 millimeters according to our feedback device. So again, we're going to have to enable our window or engage it. And then for this setting here, this is simply telling us what do we want to do with this PSO window. So we want it to be configured as a mask. We want to mask our PSO distance events. So that's what we're going to tell it to do. And again, this could be where you'd set up the bit mask if you're planning on using that. Right now, we're just doing a simple window mask. And that was all we needed to do to convert this from a distance-based firing with just simple distance-based to now we are masking those distance events. The only other thing that I added was now we plan on plotting if we are inside or outside of the window, just to show you where this window range is at. All right, let's go ahead and run this. So right off the bat, we can see because I did decrease the distance to 0.5 millimeters, we are getting a much quicker firing event. But here we can also see that in between our window, this is where our window is at, that we did set it up to be 3 to 5 millimeters. And if we put our cursors here and here and expanded the cursor so we could see between setting up our cursors and looking at the cursor data, we can see now, of course, that our window is between 3 and 5 millimeters. And if we zoomed in on this, of course, we could see, here are our PSO distance events. One occurs here, one occurs here, 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 and one just outside the window here. And like before, at each PSO event, if we zoomed in there, we have our 3 on time periods of 2 milliseconds on and now 1.5 milliseconds on firing. So 2 milliseconds total, 1.5 milliseconds on time, and 3 sets of those. So PSO is still operating as we expected. We still see all of those pulses happening in turn. So again, that was just a very simple one-dimensional PSO window mask, but hopefully that gives you an idea of, again, what exactly it's doing. And this was based on some examples in the help file. For this example here, though, we simply just needed to add our new PSO window event structure to our code to configure what we plan on doing with the window. If we want to set up the PSO window to, for instance, only turn on all the time when you're inside the window, you can do that. At that point, you're just simply reconfiguring some of the program settings. You're not using PSO window masks. You're probably not using, the distance events. But again, all of this is very modular in how you do it. You just have to remember that structure of you have to set up your events and your event structures, then your waveforms, and then your output. That concludes this motion control platform educational video. Thank you for watching, and I hope you enjoyed learning about PSO's functionality and use.